Okay, let's go ahead and try to prove Heron's formula today. So, Heron's formula states, given a triangle, any triangle I should say, okay, of side lengths A, B, and C, okay, area is given by, okay, so we would have here the square root of S minus A, S minus B, S minus C. And that, of course, is where S is defined as the semi-perimeter. Okay, very good. So let's seek to prove this now. Okay, let's go ahead and sketch a triangle here so we can see what's going on. Doesn't have to be any particular triangle, so we'll make it look like a scalene here. And we'll go ahead and label these A, B, and C respectively. Okay, so I will go ahead and label the angles as the capital letters opposing the side lengths in question. Okay, now we have proven the law of cosines in another video, so I will use the law of cosines here. Using the law of and I'm going to label this H. So using the law of cosines first, we're going to have little a squared is equal to little b squared plus little c squared minus 2 little b little c times the cosine of big A. Okay, so if I add 2bc cosine big A to both sides and subtract a squared from both sides, I'm going to get 2bc cosine big A is equal to b squared plus c squared minus a squared. And that's going to give me cosine big A is equal to little b squared plus little c squared minus a squared divided by 2bc. Okay? All right. Well, I want to go ahead and find the area because that's ultimately what I'm going to try to set equal to this right here. Area here, okay, and we're going to define it as just big A sub 1. Okay, that's going to be equal to 1/2 CH, 1/2 base times height. However, the sine of big A is equal to H over little b, which means, of course, that little h equals b times the sine of big A, which means that this becomes 1/2 BC sine of big A. Okay, which means that the sine of big A, okay, multiplying both sides by 2, dividing both sides by BC. Okay, sine of big A is going to be equal to 2A1 over BC. Okay, well, I got a couple of trig statements now. I do think what I'm going to do is define the sine of big A as a function of this here. Okay, so we're going to find a clever way of expressing this here. We know that the the cosine of big A is the same thing well, we know that the sine of big A is going to be the square root of 1 minus this squared. Okay, so we can say here the sine of big A is equal to, okay, the square root of 1 minus cosine squared of big A. And we know that's true because sine squared of A plus cosine squared of A equals 1. I'm going to put a box around that. That's a very important, the most important, I would say, Pythagorean identity. Okay, so knowing what cosine is, okay, and let's maybe zoom out one more step. Yeah, perfect. Okay, so sine of A, this is going to give us the square root of 1 minus all of this squared. So b squared plus c squared minus a squared over 2bc, all, of course, squared. Okay, very good. And we can go ahead and simplify this. We're going to have a common denominator of 4b squared c squared. Okay, so I'll be writing this as 4b squared c squared minus, and we will go ahead and keep this all factored here, b squared plus c squared minus a squared all squared over this squared, which is 4b squared c squared. Well, the square root of 4b squared c squared is just 2bc, so this becomes the square root of 4b squared c squared minus the quantity b squared plus c squared minus a squared all squared, all of that divided by 2bc. Okay, so we've got a couple different expressions now for the sine of big A. And we can set those equal to each other. Sine of big A is, after all, equal to the sine of big A. So we have as follows: 2a1 over bc is equal to the square root of 4b squared c squared minus the quantity b squared plus c squared minus a squared all squared over 2bc. Okay, let's check that and make sure we have made no careless mistakes. Don't believe we have, but let's be absolutely certain of it. Okay, looking good. And common denominator, yes, everything looks perfect. Okay. All right. So clearly we can multiply both sides by b, canceling those b's out. We can multiply both sides by c, canceling those c's out. And clearly what we have here is multiplying both sides by 2. We're going to have 4a1 is equal to the square root of 4b squared c squared minus, of course, the quantity b squared plus c squared minus a squared all squared. Okay. And now I can square both sides here. It's going to give me 16a1 squared is equal to 4b squared c squared minus the quantity b squared plus c squared minus a squared all squared. And now this right here is actually a difference of squares. Okay, I'm going to put another property up here. We're going to be using a squared minus b squared equals a minus b quantity times a plus b. Let's get a box around that. Okay, also an important property that we're going to be putting to good use here. Now, let's maybe zoom out. There we go, one step. Now, this is a difference of squares, and I can actually write this here as 2bc all squared minus the quantity b squared plus c squared minus a squared all squared. Okay? And I can actually think about this here as 2bc minus b squared plus c squared minus a squared. Okay, and then I can think about it as 2bc plus the quantity b squared plus c squared minus a squared, all and then all of that closed up. Okay, so again, just using this property, okay, factoring a difference of squares. This is not a traditional difference of squares, but it is a difference of squares. And so I can therefore think about that as a difference and a sum of the square root of each, the product of those two. Okay? All right, well, checking that very quickly. Yes, that looks good to me. So we can now think about this as follows. We can think about this as 2bc minus b squared minus c squared plus a squared. Okay? And we can think about it as 2bc plus b squared plus c squared minus a squared, like that. Okay. Well, interesting. So we've got a factored actually difference right here. We can think about this as follows. We can think about this as negative b minus c all squared. Okay, let's think about that. Check, check, yeah, that's right. Plus a squared. Okay, so let's close that up there. And then this here, we could think about that as, well, it's just going to be b plus c all squared minus a squared, like that. Okay, and checking that, yes, that's right. Okay, so kind of a little fancy footwork here. Not that bad really, but I suppose for one who hasn't seen it before, it does look a little bit foreign. But it checks out. If we think about what this becomes when we expand it, we get this precisely right here. Okay, and again, this may be a little bit more evident. Expanding this, we're going to get this right here. Okay, I'm going to go ahead and express this using the commutative property as a difference. I'm going to write this as a squared minus the quantity b minus c all squared. That's not so bad. This will keep it as it is. Okay, this is just already expressed as a difference, so we're going to keep it in there as a difference. Okay, so notice that we have a difference of squares again 2 times. We've got a difference of squares here, and we got a difference of squares here. Okay, so so yeah, here's what we're going to get. This will become, let's use a bracket there. Yep, this is going to become a minus the quantity b minus c. Okay, like that. And then it's going to be a plus the quantity b minus c, like so. Okay, that's just this part. Okay, difference of squares. Square root of a squared minus the square root of b minus c quantity squared. Square root of a squared plus the square root of b minus c quantity squared. This one's a little bit more evident what it becomes. This is just now b plus c all minus a and b plus c all plus a. Okay. All right, and we're very close indeed to being done with this. I can now think about this, of course, as A, let's make that look a little cleaner, A plus C minus B. Well, let's just write it in there as A minus B plus C. Okay, this, of course, is A plus B minus C. This, of course, is negative A plus B plus C. This, of course, is A plus B plus C. Okay. Now, I think one more zoom out. There we go. This is all equal to 16a1 squared. So we're going to go ahead and divide everything through by 16. Now, 16 is 2 to the power of 4. So I can think of a1 squared as equaling, and I'm going to write it out like this, a plus b plus c over 2 times a minus b plus c over 2. So 2 times 2 is 4, and then times 2 again, 8, and then times 2 again, 16. So then it's going to be a, we'll do a plus b minus c over 2, and then, of course, negative a plus b plus c over 2, right? So 2, 4, 8, 16, and then we're just going ahead and grouping these accordingly. Now, a plus b plus c over 2 is just s. That's all. That's what we've defined it as. A minus b plus c over 2. We're going to write this here: a minus b plus c over 2. This is just going to be s minus b. Okay, let's get that in the box. Okay, a plus b minus c over 2. This is just, of course, going to be s minus c. Okay, get that in the box. And then negative a plus b plus c over 2. This is just s minus a. Okay, so we'll get that in a box. Okay, so we are basically done here. And we can just now take the square root of both sides, and we can see that a1, which is the same area that we've defined that we're trying to show is equal to all this, is going to be the square root of s. We'll go ahead and write this out here as s minus a, and then this, so s minus b, and then this here, s minus c. So there you go. A little bit of work involved, but not so bad. Hopefully you enjoyed this video. Hopefully it helped you understand not just how Heron's formula works. I'm sure most of you out there know how it works, but most importantly, why it works. We love proven math statements. We love proven physics statements. Please leave comments, questions, concerns, and of course, recommendations for future content. Have a great night, and we will see you in the next video.